To get started, sort of a heads up, we've got a test coming. It's still 2 weeks away, so it's going to be, it's actually a little over 2 weeks. It's 2 weeks from Thursday, 15th. So keep that in mind. It's going to be covering the last few chapters, basically what we've done since the last test. So acid base, redox, and then today we're starting into chapter 20, which is electrochemistry. The study guide will be up on LNS soon in the next couple days. And yeah, so just keep that in mind. We've got that coming up. We are actually getting very close to the end of the year. We only have about 8 more weeks of actual class instruction. And we've got the test on the 15th, and then we've got the final, like May 18th, I think it is. So, like I said, we're going to start into chapter 20. This will be the last chapter before the test. After chapter 20, we get into organic chemistry. Organic chemistry has a lot less math in it. So if you hated the math, organic chemistry has a lot less. The trade-off, though, is that there's more to memorize, more to remember. So it's kind of good news, bad news there. Anyway, you don't need to worry about that until after the test. So, chapter 20, electrochemistry. Electrochemistry is basically, we're going to apply redox. We're going to be taking these principles that we talked about in chapter 19, and we're going to put them to some real world use. Okay? So to start out, the book kind of poses this question. Okay? So it says, when we deal with redox, we've dealt with half reactions, where you break it down into, well, this is the reduction part and this is the oxidation part. So it says, well, what if you had 2 different beakers and you take one and you put everything that is with the reduction in, you take the other one, you put everything that has the oxidation. So you know what would happen? Well, nothing would happen because they're separate. Okay? But there is a way that we can keep these things separate, but still get a chemical reaction happening. Now, remember, so if we draw this, so let's say we've got a strip, what is it, it's copper and zinc, I think. Yeah. So if we have, this is solid zinc, and in solution, we have our zinc ions, and it's a 2+ ion. And then over here, we have a solid strip of copper, and once again, we have copper ions. So just like that, nothing's going to happen. But remember, redox is all about moving electrons. Well, if we could somehow get electrons to move from this side to this side, we could potentially start to get some redox. And so what we do is we take a wire and we connect these two metal strips. It says it's copper wire. Really, any wire that will allow electrons to move is going to work. Copper is very common to use because it actually allows electrons to move very readily. It's also why we use it for electricity wiring. Anyway, so now electrons can move between these. Okay. Now, it's still not quite ready to go. When we first attach the wire, we may start to get some reaction, but it won't go really very far at all, because what's going to happen is we start to get some charges building up. Okay. So what happens, the electrons are actually moving this direction. Okay. And what's going to, happen, in order to lose these electrons, this solid zinc has to become zinc ions. So we're getting more and more zinc ions here. And in order to accept these copper ions actually are going to come out of solution and start to build up on this copper strip right here. So what happens is we get this, imbalance of charges. So we got to find a way to solve that. And the way we solve that is with a device called a salt bridge. So basically it's a tube that is sort of U-shaped, and we put it into both sides. Now we have like a gel in there, so these actual solutions can't go up and travel through there. But we have a salt in there. I think the one in the example they use, potassium chloride. So since we have positive ions that are building up here and positive ions that are going away there, that means, so in order to offset these positive charges, the chlorine is going to come out here. And it's going to keep things neutral. It's going to allow this to keep going. And then the potassium will come out on this side because we're losing those positive charges. And so we need to replace them to keep things, once again, neutral, so that this will continue. Okay. So here we have what is called an electrochemical cell. So we've taken our two half reactions. We have our redox and we have our reduction and we have our oxidation. Okay. So that means, we've separated these, and since we've separated them, we can make the electrons move right here instead of right together in the same beaker. If we put all of this together in the same beaker, we're going to get the redox reaction, but the electrons aren't going to be moving through the wire. Now, the reason why we want them to move through the wire is because, moving electrons through a wire is electricity. We can take chemical reactions and generate electricity. That's the whole point of this. Okay. Now we'll talk about other situations where we will use electricity to make make a chemical reaction happen. So we can actually use the electricity from a different source to make a reaction happen. But if we just let it go spontaneous, okay, we're going to be generating electricity just by the fact that we have separated this zinc ion solution, copper ion solution, and connected them with a wire and a salt bridge. Okay? It's spontaneously going to generate electricity. It has the potential to do that. We're generating electricity. It's specifically called a voltaic cell. It's named after Alessandro Volta, who is credited with inventing them. There's an example of, it's a replica, it's not actually one of his, but it's on page 709 in the book. We have zinc and copper in alternating disks so that they will move the electrons through. So anyway, the whole point of this, voltaic cell is to separate these reactions into one side is reduction and one side is oxidation. When we are dealing with these, we have two specific words that we're going to talk about. The anode and the cathode. Okay. The way it works is wherever we're seeing the reduction, okay, and if we look at this, and we say, okay, well, electrons are moving this way towards the copper, we're getting copper ions that are becoming solid copper. So we're gaining electrons here. So this is the reduction, which makes this the oxidation. We also say that one is going to be the anode and one is going to be the cathode. The way that, well, there's one way that you can remember which is which. For oxidation, the anode, and for reduction, the cathode. Okay. So oxidation has an A in it, anode, reduction has a C in it, cathode. Okay. So in this cell, this right here, this zinc side is the anode, the C side, or the reduction, this copper side is the cathode. So like I said, this is spontaneous. Okay? We don't have to do anything other than just hook everything up correctly. But we can change what metals we're using. We can change which metals we're using, and that sort of changes the situation. We learned early on, some things are more reactive than others. But there's a pattern that we can follow. Okay? The book talks about potential energy and kinetic energy with roller coasters. Okay? So obviously, if you're at the top of that very first hill on a roller coaster, you've got a lot of potential energy. Okay? You built up that potential energy as you went up the hill. But when you're at the top of the hill, you always know you're going to go down the hill. Okay? There's never a chance that you're at the top of the hill and then all of a sudden you just start going up further into space. Okay? we always know that you're going to go from the high point, move towards the low point because of gravity. Now, some roller coasters are higher than others. Okay, so exactly where you start to go down and how fast you go depends on how high the roller coaster is. Exactly where the electrons move and how much force is behind those electrons, well, it depends on what metals you use. Okay? So obviously, as chemists, we want to put specific numbers with that. We want to be able to say, okay, this one has, X amount of potential to gain electrons. Okay. So we call that a reduction potential. And we have a number, okay, that says this is the potential this particular metal has to be reduced. Okay. Now, obviously, we have to measure that at specific conditions because, well, if we've learned anything from chemistry, it's that if you change the conditions, the reaction is going to go just a little bit differently. For one thing, we have to pick something to measure it against because you can't have reduction without oxidation. So we need to have something that we're going to pair it up with. And we always want to have that same thing so that when we compare different metals, we'll get, a valid result. If you don't pick the same thing, you are not comparing them accurately. So what we have picked is what we call the standard hydrogen electrode. So hydrogen can actually be reduced. The half reaction looks like this. Okay. So it's being reduced, gaining the electron. Okay. Now we measure these reduction potentials in volts. Okay. If you look at our unit poster over there, it says electric potential. The derived unit is the volt, okay. Which we can go through the other equivalent SI units, watts per amperes, and then you can go watts per joule seconds, ampere, get all that. But anyway, we measure it in volts, long story short. So what we can do, we can pair up any of these half reactions to the hydrogen electrode. Now, I'm not going to ask you to memorize this, but just for your information, the standard hydrogen electrode has a small piece of platinum in a hydrochloric acid solution with the hydrogen ion concentration at 1 molar, and it has hydrogen gas at 1 atmosphere being bubbled through there, and it is at 25 degrees Celsius. So, like I said, I'm not going to ask you to reproduce that on a test, but just for your information. Now, we picked this and set the value to 0 volts. Okay. This has a reduction potential of 0 volts. By the way, we call that E naught. So the reduction potential, E naught, 0 volts for the standard hydrogen electrode. And then, like I said, we pair it up with these other half cells. One really nice thing about this standard hydrogen electrode is that it's sort of right in the middle. This can actually happen the other way around. And be oxidized. And it depends on what you pair it with. If you pair it with something that really wants electrons, well, it's going to pull those electrons away from the hydrogen. But if you pair it with something that's really ready to give up electrons, then it's going to be reduced there. Okay. Now, there is a chart on page 712 with a whole bunch of standard reduction potentials. And obviously, you know, everything has to be standardized to get this to work properly, but that's what we get. So luckily, people have already done this work for us, and we can just look at this chart. Okay. Now, these are all written as reductions. Okay. But obviously, one of them has to be an oxidation. One of them has to be an oxidation. So what's going to happen, even though they're all written as reductions, when you pair them up, like I said, depending on which you pair up, you can change the way these electrons move. Now, in this case, if we look at the zinc half reaction here, the value for that reduction potential is negative 0.7618 volts. Okay. And if we look at copper, that one is positive 0.3419 volts. Okay. What you'll notice is this is a lower value. Okay. It's a lower value, and that is going to be the one that is oxidized. Okay. Whatever has the lower value, that's the one that is going to end up giving the electrons. Whatever has the higher value is going to take the electrons. Now, we can find a higher value than copper. For example, well, let's just pick one here. We'll pick silver. Actually, let's pick mercury. That one, we like mercury. So if we were to pair copper and mercury, the mercury has a value of 0.851. So in that case, copper would have a lower value, and it would, instead of being reduced, it would become the anode and be oxidized. So when you pair them up, the one that has the lower value of whatever it is that you're pairing, okay, you can make any combination of two of these things on this chart. Okay. And whichever one has the lower value is the one that is going to instead of being reduced as written on the table, it's going to flip around, reverse, and be oxidized. Okay. If you notice, all of these reactions are written as reversible. Okay. They can all flip around. So here we have, like I said, we're lucky that somebody else did all of this calculating. Okay. Keeping these things at the proper concentrations and everything to do this measurement. So, one note, now I don't do this very often, but you may see it here, something called cell notation. Like I said, I don't really use this notation much, but you may see it. So I want you to be aware of what you're looking at. Okay. What we do, we take the oxidation half cell. Now the book has given the example of we're pairing copper with our hydrogen. Okay. So in this case, because copper has a positive value and hydrogen has a 0, hydrogen is going to flip around. So it becomes the reduction. And then copper, it stays this is going to be the oxidation. I think I may have said that wrong. This is going to be the oxidation, and then copper will stay the reduction. Now, when we write the cell notation, what we do, first we take the oxidation. We write the reactant, draw a line, and we write the product. Okay. It's our oxidation. Then we write 2 lines, and now we go to the reduction. Once again, we start with the reactant, draw a line, and the product. Okay. So that is cell notation. As I said, I don't use it very much, but it is important to notice that. Now, this would be how we determine the standard reduction potential for copper. Okay. And how we would determine it for any of those other metals in that chart. But once we have that, then we can go straight to comparing, well, copper and zinc. Let's stick with that. Okay. So we have copper and zinc. And if I erased the numbers, so let's find them again here. So for copper, our E0 copper is that. And then E0 zinc, okay. So there we have the calculated E0s for each individual as compared with hydrogen. So what is the E0 of that entire cell, the copper and the zinc? Well, the way that we calculate that is the E naught of the reduction minus E naught of the oxidation. So we need to know which one is going to be the reduction and which one is going to be the oxidation, but we already figured out how to tell that, okay? Remember we said whichever one has the lower value, that one's going to flip around and be the oxidation. So for our copper zinc cell, to find the total potential, we have the reduction, 0.342 volts, minus the oxidation, negative 0.762 volts. Remember, when we subtract a negative, we get the opposite. We are actually adding. So what we end up with as the total reduction potential for this cell, 1.1044 volts. Okay. So whenever you compare these two standard reduction potentials in your cell, this is how you're going to calculate the total potential for the cell. And you take the reduction potential for what's actually being reduced and subtract the reduction potential for what is being oxidized. Okay. I want to double check. I believe I put that equation on the front of the test, but let me just look at the test before I. Yes, so it's right there on the test, so you don't have to memorize that, as long as you can remember that that's the equation you need to use. So let's do this example problem again, because I want to make sure we can do this. So in this case, let's clean everything up here. We're no longer going to be calculating copper and zinc. We've moved on, and we've got two different substances here. Okay. And I keep saying metals. They don't have to be metals. For example, we're using iodine here, which isn't a metal. But anyway, most of them are metals. So here we have our iodine. And we're pairing that up with iron. Okay. So the question says, determine the overall cell reaction and the standard cell potential. And then it says to describe the cell using cell notation. Anyway, so we need to determine the overall reaction. So we want to first look up the standard reduction potentials, because we need to know which one's going to flip around to be oxidized. So if we look, the E naught for iodine is 0.536 volts. The E naught for the iron is negative 0.447 volts. So in this case, iron is going to have the lower reduction potential. Okay. So the iron is going to flip around and be oxidized. So what we're going to be dealing with is actually that. So to write the entire equation, the entire reaction, we just add this to this. Now we could keep those electrons in there, but we know they're going to cancel out because we've got 2 electrons over here. We've got that. So that is our overall reaction. So, standard cell potential. Well, the good news is we already have what we need. And so we take the E naught for the cell is equal to the E naught for the iodine minus the E naught for the iron. So that, and this gives us a total standard reduction potential of 0.983 volts. Okay. And then the last thing it asks for is cell notation. We'll do that just because. Remember, we do the oxidation half reaction first, which is this one here with the iron. That's the one that flipped. So they are reactant, line, product, double line, go to our reduction, reactant, line, product. That's cell notation. So. Okay. Now, if we can look at just, one last thing before we finish up for the day. Basically, the last sort of thing that it talks about is determining whether a reaction is spontaneous as written. And so we basically do the same thing. We just have to add one more step of analyzing just at the end. It's a really fast step, so don't stress. Let's look at this problem here. So the first thing we have to do is determine what are our half reactions. Okay. Now with this one, I'm going to break it into all right, 2 plus is 6 minus. Now, we could go through and assign a whole bunch of oxidation numbers to figure out what is being oxidized and reduced. But if we look at this, you can see it's going from 2 plus to 0. So this is gaining electrons, which means this is the reduction. Okay, so we know that this is written as the reduction, and that's the oxidation. Anyway, so if we look at our chart again, and we find our cobalt 2 plus, which is right here. That, as the reduction, has a value of negative 0.28. And this here, remember this is oxidation, so when you're looking at the chart, you have to flip it. You have to be looking for this as the reactant. So we find that right here. And that is positive 2.010. So now, all we have to do is figure out the E naught of the cell. So, E naught of the cell, remember, is the reduction, which is this one right here, negative 0.28 minus the oxidation, which is this one here, 2.010. And so our total E naught as written is going to be negative 2.29. If you calculate the reduction potential and as written, it's negative, that means it's not spontaneous. If you get a negative reduction potential, I would always double check and make sure that you did your math correct and that you didn't flip and do oxidation minus reduction. But as long as you did that, then you can say, no, this is not spontaneous as written. In fact, it would be a spontaneous reaction in the opposite direction. If you mix these things, you are going to get redox, but our sulfate is going to be what's being reduced, whereas the cobalt will be oxidized. So, okay. And that is section 1. So hopefully it wasn't too overwhelming. I know there was a lot of moving parts, but a lot of that was sort of just kind of background information. The calculations right here, okay? Remember, whichever one has the lower reduction potential, it's going to flip around and be oxidized, be what's oxidized, and then use this, and that's going to tell you your overall reduction potential. So we'll stop there and let's get started on some homework.